Hi girls, how are you? Just a quick introduction today into our final chapter, which is to do with pH and calculating pH and that kind of thing. So this is kind of the second part of an acids-based topic, which we introduced early days in fifth year. When I say early days, it's probably just after Christmas, before we would have done acid-based titrations. So a good place to start would be to look back over some definitions. I've just written them out very crudely for you here. You should know what an Arrhenius acid is, an Arrhenius base, and a Bronsted-Lowry acid and a Bronsted-Lowry base. They're important definitions. An acid forms a hydrogen ion for Arrhenius, a base forms hydroxide ions, and we talked about why that doesn't work for everything, for example, for ammonia, and for particularly low pHs, it doesn't work. And it also doesn't work for solutions that are not aqueous, that are not based in water. Okay, so a better definition came along later, which is Bronsted-Lowry's definition, which is that acids are proton donors and bases are proton acceptors. And we did a little bit of work on conjugate pairs, which you may want to look at again. Okay, so that's very much a fifth year thing that we did at the time. There's some notes in your folder to look at that, if that would be a good place to start. So today might be a good day to dig that out. From that, we're going to look at two things that are very important. The first one is something called Kw, which is a dissociation constant of water. Okay, we're going to explain that today in this clip. And we should know what pH is. Now, pH is something you've come across before as far back as junior cert, and you know that it's a scale that measures acid and base. But certainly in terms of what we've done together, you don't know where it comes from and what it really means. So we're going to look at that today as well. Okay, you may well know that already, but in terms of what we've done, we've kind of just defined it as an arbitrary scale that goes from 0 to 14. And the exact definition is here, the negative logarithm to the base 10 of the hydrogen ion concentration, okay? Again, we'll explain that later and why that's used, why it's between 0 and 14. Hopefully that makes sense, okay? Or it will make sense in the next couple of minutes. Right, but they're important definitions. Again, this is a topic a little bit like equilibrium, where there aren't a huge amount of definitions, so it's a good idea to go over them and make sure you know them. This often forms half a question in 10 or 11 and is definitely a handy one to know. Okay, so really what we're looking at today is what is Kw and what is pH, because those two things are linked. So we're going to look at that, okay? Now to look at that, I want you to look at this diagram here, which is a beaker of water. Okay, and I've highlighted or I've drawn two of the molecules of water here like this. You can see them there, okay? And as you know, or as you should know, water is a polar molecule, okay? So oxygen is very electronegative, hydrogen is electropositive. These pairs of electrons are not shared equally. You can see I've drawn in the delta minus and the delta plus there, and you should also be aware that there are two pairs of non-bonding electrons on the oxygen, which is why it's V-shaped, okay? So that should be old news to you now at this stage, related to bonding. If you're not sure about that, look over the bonding notes that we did and a couple of the bonding work that we've done in the past, right? But the point is that there's a strong intermolecular force between this hydrogen and this oxygen here, attracting them. All right, now it turns out that in pure water, a small amount of these hydrogens, you're out of focus there, I'm out of focus, sorry. These hydrogens actually break off and form a bond with their neighbouring oxygen. So that kind of looks like this. It leaves behind its pair of electrons and it forms this thing here, H3O+. Can you see that? And leaves behind an OH-. Now, this doesn't happen to all the water molecules. In fact, it only happens to a tiny, tiny amount. But in any pure water sample, a small amount of these molecules undergo this process, sometimes called dissociation. Okay, again, that's a word we would have come across in fifth year. And this is called an oxonium ion, okay, or a hydronium ion sometimes, right? That's really what acids do. They're proton donors. This is water behaving as an acid. It's a proton donor, okay? So we can write this in terms of a chemical equation like this. Two H2O molecules dissociate or break apart into H3O+ and OH-, like that. Now it turns out that this should look familiar to you now from what we've done in equilibrium, okay? Because this is a reversible reaction, okay? And it's a species that forms a process where we can get a value for K, okay? So there's a system of dynamic equilibrium, and this becomes a constant. So we can write that like this. Let me just dig it out here. There, okay? So Kw is a constant. In water at 25 degrees, we know what the value of this number is. I'm going to tell you what it is in a couple of minutes. But we can write this equation here, the products over the reactants, H3O+ over OH- divided by H2O squared from our knowledge of equilibrium, which you've just done, right, will give us a constant. Okay. However, we can simplify this, and I'll show you how. Because if this constant is expressed in moles per litre, well then the value of H2O here is 1, isn't it? Because that's the total concentration of the water. All right, so water is obviously 1 if there's a litre of it. So let's assume there's a litre of it, and in that value is now 1. So that means we can basically get rid of everything on the bottom of the fraction and say that we've now got this value of Kw, which we know is H3O plus multiplied by OH minus. Okay, we've got rid of the bottom part of that equation because it's equal to 1. However, we can simplify this even further, because if we look back at our diagram, you'll see that for every one of these OH minuses, there's one of these H3O plus. We can't have one of these without one of these. Every time one of these is formed, one of these is left behind. In other words, the concentration of this must be the same as the concentration of this. So the concentration of H3O plus is equal to OH minus. Makes sense, doesn't it? Yeah. Okay, so we can simplify this even further. We can say that Kw is equal to H3O plus squared. In other words, we can get rid of this term because it's equal to this term. So we can just write it as H3O plus squared, okay? And like I said, we know what that value is. It's 1 by 10 to the minus 14, okay? So scientists have calculated this. They know how much in a pure sample of water, how many molecules of that are dissociated, what the concentration of that dissociation is in moles per litre, and it's 1 by 10 to the minus 14. That's the value for this equation here that we have at the top. All right? So that means that we can calculate the concentration of H3O plus by getting the square root of that, and that's 1 by 10 to the minus 7. Now what this tells us is, this tells us the concentration of the amount of water molecules that have dissociated, that have acted as acids in any pure water sample. Okay, so in any pure water sample, the concentration of water that's actually been acidified, okay, that had a proton added to it, the H3O plus, is 1 by 10 to the minus 7. Now the problem with 1 by 10 to the minus 7 is it's not a very handy number to use. Sure, it's not. It's quite cumbersome. It's quite difficult to imagine that. Obviously, it's very small. So oftentimes in maths and in science, when we're using very large and very small numbers, we use a log scale. We've mentioned this before. Okay, we use a log scale. You may have done this in maths. And to make life easier, we use a minus log scale because this is such a small number. We're using minus integers there. So when we get minus the log of 1 by 10 to the minus 7, the value that we get is 7, which is obviously a nice, easy, handy, round number for us to use. Okay, and this is our standard that we use for pH. In a neutral solution, the amount of acid present, the amount of water that's donated its proton to behave like a hydronium or oxonium ion is 1 by 10 to the minus 7, and the minus log of that is 7. So it's a neutral solution. Now, if it's an acidic solution, that means there are more of these present. The more of these, the greater that number, the less the minus the log of that number. In other words, the lower this number. If there's fewer of these present, the lower this number, the greater this number is here. Okay, so that's where we get this scale from 0 to 14. Now this is important because they sometimes ask you for a definition of Kw and how do you get Kw? How does it arise? So it's important that you can describe these steps. Again, we'll talk about exam questions later. Today we're just introducing the concept of what Kw is and what pH is. This is pH. It's a standard that we use. It's the amount of water that's behaving like an acid. Okay, it's the concentration of that water in moles per litre that's acting as a hydronium ion. Of all those millions and millions and millions of molecules in your litre of water, this is the amount of them that have accepted a proton and behaved like an acid. And when you get the minus the log of that, that's where you get 7 from. Okay, so if this solution was to increase, that would mean you have an acid solution and this number would be lower. If this solution, if the concentration of H3O plus was to decrease, this number would decrease, you'd have a base, and this minus the log number would be higher. That okay? So today, I just want you to go back over those definitions that I mentioned at the start, have a look through this process, and we'll start to look at how to actually calculate acids and alkalis tomorrow. Okay, hope that helps. Bye-bye.